Welcome back, Pre-Calc Plus students. Today we're going to continue on with section 3.2 on log functions and their graphs. So we're going to start off with what the definition of a log is, and the base again is going to be a. X and a are both going to be greater than 0, okay, so no negatives here, and a cannot be equal to 1, because remember, if our base is 1, 1 to any power is just 1. So if we have y equal to the log base a of x, this means if and only if. It means that x would be equal to a to the y. So when we calculate the log, if I'm taking the log of something, the log base 2 of 4, what I'm actually doing is finding the exponent. I always remember it that way, that this y is the exponent of the exponential form. A is our base. So it's the base here for the log, it's the base here for the exponential. And then x is either the number that follows the log, or x is equal to a to our base to our exponent. So the way that we read this is y is equal to the log base a of x if and only if x is equal to a to the y. Okay, so it's important that you say base. If you just say log A sounds like base 10, and we'll talk about that more later on. But that word base in there, that's important. Okay, so if I have this expression, there's the way that it's read, log base A of x. And remember, what it means is a to what power equals x. Okay, that's a quote, not a, looks like a power there, but that's a quote. So a to what power is equal to x. That's the phrase that should go through your mind when you see this expression. So if you're asked to evaluate a log, so here I have log base 3 of 81. So what's going through my mind is 3 to what power equals 81. Okay, and that means that it would be 4, because 3 to the 4th is 81. When I see this one, I'm thinking 2 to what power is equal to 1/16. Now, because this is a fraction, I know it's going to be a negative power. So I'm thinking about what 2 to what power is 16? It's 2 to the 4th. So in this case, it's the negative 4th to make it reciprocate. For this one, I have a decimal, but this is 1/100th. And here, this is what I was talking about. When there's no base written, it's understood to be base 10. We call this the common log. So that's base 10, which is also known as the common log. And this is the one that you see on your keyboard of your calculator. There's usually, a log button. So for this problem, my base is 10, so I'm thinking 10 to what power is equal to, this is 1/100th. So again, I know it's a negative exponent to turn it into a fraction. So 10 to what power is 100? That's 2, so it's the negative 2 power. Properties of logs. So here we have log base a of 1. So I'm asking myself, a to what power is equal to 1? Well, we all know any base to a power of 0 is equal to 1. So log base a of 1, so that means a can be any base. If I have the log base a of a, that means a to what power is equal to a? That would be the first power. The log base a of a to the x is just equal to x. So what I'm really being asked here is a to what power equals a to the x? It would have to be the x power. Let's go down and do this one next. If log base a of x is equal to log base a of y, then, so if we have same bases, the only way that's going to be equal is if x equals y. Lastly, we have this one. This one looks a little more complicated. It's a raised to, this is the power, log base a of x. So what would that equal? So if I take this and I randomly set it equal to another variable, we'll just set it equal to, I'll use a capital N. And if I'm going to solve for n, this is exponential form. So what I'm going to do is take the exponential form and switch it back to my log form. So in log form, it would be log of my base, which is a, of something, n is that something, equals my exponent. And the exponent is log base a of x. Now we can use this one-to-one property because we have log base a and log base a. So that means n is equal to x, which means this entire thing was equal to x. So when you have, this again is exponential form, so when you have a base raised to a log of that base, whatever comes after that is what that expression is equal to. Okay, the natural log is base e. So again, that number e, that is a useful number, okay, in exponentials and logs. So we give it its own expression. Instead of saying log base e, you never hardly see it written like this. I've seen it a couple times in textbooks, but you don't usually see it like this. You usually see ln, that's what a lot of students say, ln, or natural log of x. And this is also a key that you should see on your keypad on your calculator. So if we run through the properties, now when I see this, when I see natural log of 1, I'm picturing this in my mind. That's log base e. So what I'm being asked here is e to what power is 1? Well, this is just like before. Anything to the 0 property, power is equal to 1. ln of e, that means e to what power is e? That would be the first power. If I have the natural log of e to the x, that means e to what power equals e to the x? That would be the x power. If we jump down to the one-to-one property, if we have the natural log of x equal the natural log of y, then x must equal y. And then lastly, we'll go back to this one. This is a lot like this a to the log base a of x, because remember, this means log base e of x. So e raised to the natural log of x is just x, for the same reasoning of what we did back on this example. Okay, let's see what else we have here. The graphs of logs. Okay, so if I were to graph y equal to log base 2 of x, now you have your calculators. So the important thing to keep in mind, it depends on how old your calculator is. Some of you, when you press log, you may get the form where it lets you put in the base. Okay, it lets you put in the 2. So it's very simple to just do log base 2 of x. If you have an older calculator like I do, I have to use the change of base formula. So for change of base, I'm going to show you that now so that you can enter these into your calculator. If I have, I'm going to do it in general, log base b of m. The change of base formula says we can rewrite this as the log of m over or divided by the log of b. And that's how we would enter this into our calculator. So if I want to see the graph of log base 2 of x, I would enter this into my y1 as log of x divided by, so use your division symbol, log of 2. Okay. So when you graph that, remember logs and exponentials are inverses of each other. So the graph of the log is going to have symmetry with the graph of the exponential. It would have symmetry with 2 to the x. Remember, 2 to the x looked something like this, right? Crossed over 0, 1, and then soared upward. So if 0, 1 is on the graph of the inverse, then remember 1, 0 is going to be on the graph of our log. And then I could plug in some numbers that would be easy to calculate. You can do one of two things. Plug in numbers for x that are very easy to calculate, meaning they're 2 to some power, right? Or you can set up a chart. Again, you probably really won't need to do this much because you're allowed to use your calculator. But if I were doing this by hand, I would probably rewrite this using my exponential form. So in exponential form, this is my base, right, to my exponent, which is y, equals x. So when I do my xy chart, rather than finding values of y, I would plug in values. Rather than doing values of x and solving for y, I'm going to plug in values of y and solve for x. So if I started with, remember we don't have any negatives, so if we start with 0, 2 to the 0 is equal to 1. And there's our intercept. If I plug in 1, 2 to the 1 is 2, so I have the point 2 comma 1. Let me take this other one out of here so we don't get confused. That was from the exponential. And then if I plug in 2, 2 squared is 4, so x is 4. So if I go out 1, 3, 4, I'm up to 2. And then if I do 3, that would be 8. So 1, 2, 3, 4, I'm up to 3. Now let's see what happens between 0 and 1. If I plug in, let's see, what do I want to plug in? If I plug in a half, then 2 to the 1/2, remember that means the same thing as square root of 2. Which, oh, what am I doing? I'm going the wrong way. I'm sorry. I want a value of x that's between 0 and 1. Okay, so I have to think the other way. So if I plug in 1/2 for x, let's do that. Oh, I know. I'm sorry. I left out the negatives for y. So if I plug in, let's say, a -1, 2 to the -1, that would give me the 1/2. So I have 1/2, -1. If I plugged in -2, that would give me a quarter. So I'd have 1/4, -2, and so on. So what's going to happen is these points are going to keep getting closer and closer to the y-axis, but they're never actually going to touch it. The y-axis is an asymptote. So the graph would travel along there. It's going to come up, and it's going to start to look like it's leveling off, because after this point of 8, 3, now I'd have to go all the way out to 16, right, to go up to 4. So it is still increasing. On your calculator, it may look like it flattens out, but it really doesn't. But along here, it will look very flat because it's going to travel right along that y-axis but not touch it. So that's the basic shape of the parent function of any log graph, which again is a reflection. Remember how our graphs reflect when they're inverses. They reflect over that line y equals x. The exponential graph looked something like this. So if you plotted log base 2 of x and 2 to the x, both on your calculator screen, you'll get a nice picture of that symmetry. Okay, let's talk about the transformations of the graphs. So here we have log base b of x plus c. So that c, there's a big difference whether if we have parentheses or not. Without the parentheses, this is going to shift the graph upward. So it's just like an x squared plus 4, or any parent function. This is the parent function. When we add on to that parent function, that's a move upward. So it's going to go up c units. So if it's, again, no parentheses but a minus c, this would be down c units. With the parentheses, this is the horizontal shift, and it's always opposite of what we think. So if it's x plus c within the parentheses, this goes to the left. And if it's a minus c, it goes to the right. So again, without parentheses is up or down. With the parentheses is left or right. If there's a negative out front, that's a reflection over the x-axis. And if there's a negative right in front of the x, then this would reflect, I'm just going to put quotes to copy down, reflect over the y-axis. Okay, so we have two examples here. You're asked to find the domain, the x-intercept, and the vertical asymptote. So remember, initially the vertical asymptote was the y-axis. So if that graph moves left or right, the asymptote is going to go along with it. Initially our x-intercept was 1, 0. So same thing, if it shifts left or right, then that x-intercept is going to go along with the shifting. Okay. The domain, that also depends upon the vertical asymptote. When we look at the original graph, the domain is from 0 to infinity. So if the graph shifts left or right, then the domain is going to change accordingly. If we have shifts of upward or downward, that's not going to change the domain. Okay, so let's take a look at these. So here, for example, we have that shift downward, right? This is going down 2 units. So actually I cheated and did these on Desmos already. Oops. There we go. There's the right graph. Okay, so let me shut this one off. So we have log base 2 of x minus 2. So here's that graph. Okay, so you can see what happened here is the intercept changed. Okay, our intercept is at 4, 0. Now I'm going to show you algebraically how we get that new asymptote, or I'm sorry, new intercept. So if we start off, to get any x-intercept, we want y to be 0. So if I plug in 0 for y and then solve for x, I have this equation. And this is where things are kind of a little backwards in this chapter. They expect you, the only way to get intercepts is to do a little solving, and we haven't discussed solving yet. So we're going to do a little bit of basic solving here. You're going to isolate the log. So we want to add that 2 to the other side. So we get 2 is equal to the log base 2 of x. So now if we switch this into exponential form, 2 is our base. We're raising to this power, which is 2 also, and that's equal to x. So x is equal to 4. So that's how you would get that x-intercept algebraically, if that's what you need to do. If you're allowed to use your calculator, then you can just get the intercept from your calculator. Now the vertical asymptote, if we go back to that graph, as you can see, the asymptote is still, this is still traveling right along the y-axis. Oops, sorry. It has it going right down along it, okay, but it's not crossing it. So the asymptote is the same, it hasn't changed. And if the asymptote's the change, it hasn't changed, then the domain hasn't changed. So for both of those things, the domain would be still from 0 to infinity, and the vertical asymptote would still be the vertical line x equal to 0. Now for this one, those things are going to change because now which way are we shifting here? If it's x minus 6, that means we're going to the right, right? So if we're shifting to the right, then the asymptote's going to shift to the right, the intercept's going to shift to the right, and the domain is going to change. Okay, so let's go back to the sketch of the graph. So this time I'll shut off this one and turn this one on. So now this is another important thing to bring up. So here, even on Desmos, it stopped doing the sketch. This graph doesn't end here. So keep that in mind when you're looking at these at your calculator. What I've been told is sometimes the values just get so small or whatever it is that they can't, the calculator can't compute them anymore, or I'm not sure what it is, but it's not uncommon to see a graph stop like this on your calculator. But keep in mind, you have to know that it does not stop there. This graph will keep on going upward, okay? So the reason why it's this shape is because of that negative. There's that reflection in the x-axis. It also shifted 6 units over to the right. So if we take a look at this, our scale is by 20s. Okay, so remember it was at 1, 0, and this does look like it's out about 7, which it should be. Yep, there it is, 7, 0. So let's see how we would find that algebraically. So again, if I set this equation equal to 0, so right now this is as if I have the log isolated. Okay, it's different here. I had that minus 2 hanging on to the log. This is a part of the log, the x minus 6. So I'm actually ready to go right into my exponential form. The negative I can pretty much disregard because if I divide by -1, 0 divided by anything is still 0. So I can just disregard that. I'll go right into my exponential form. So it's 5 to the 0. So 5 to the 0 is equal to x minus 6. And now I can drop the parentheses. Anything to the 0 power is 1. And then when I add that 6 to the other side, I get the 7. So there's my x-intercept, x equal to 7. Since we shifted 6 units to the right, that means the domain is going to be greater than 6. So it's from 6 to infinity. And the vertical asymptote is now the line x equal to 6. So let's just take a look at the sketch one more time. So again, here's that vertical asymptote traveling right along x equal to 6. Okay, and we can see all of the points of this graph are from 6 on up. Okay, so that gives us the domain. Okay, so that concludes our lesson for 3.2. If you have any questions, you can join me on Zoom from 11 to 12. The information for that, the link and the password are on the website. And I hope that you have a good day, and I hope everything's going well with you. So if you have time, check in with me on Zoom. I'd love to see you guys. Have a good day.